Hello learners, on behalf of Indira Gandhi National Open University, we welcome you for this video lecture session. Today's topic is gas cycle refrigeration. This is 38th module of the course Thermodynamics and its application. I am Subhashish Maji, professor from School of Engineering and Technology of Indira Gandhi National Open University. So, dear learners, let us begin our discussion on the topic gas cycle refrigeration. After listening to this video lecture, you will be able to understand the concept of gas compression refrigeration system. You will be able to know the BRAYTON or JOULE cycle. You will be able to explain the reverse BRAYTON cycle, and you will be able to solve the numerical related to gas compression refrigeration cycle. So, dear learners, let us begin our discussion on the topic gas compression refrigeration system. Gas compression refrigeration system is mainly used in liquefaction of gases. In such a case, the gas to be liquefied is compressed to high pressure through multi-stage compression, cooled in heat exchangers at constant pressure, throttled to very low pressure, and the resulting liquid and vapor are separated. A particular type of this refrigeration system with air as the working substance, known as air cycle refrigeration system, is a popular system used in cooling aircraft cabins. Such a system works on reverse BRAYTON or JOULE cycle. BRAYTON cycle being the ideal cycle on which a closed cycle gas turbine power plant works. So, let us first discuss about the BRAYTON or JOULE cycle. The BRAYTON or JOULE cycle is shown in figure 1 is the ideal cycle on which a closed cycle gas turbine power plant operates. Figure 2 gives the cycle on TS diagram on which the plant operates. This is the BRAYTON or JOULE cycle. So, this is the schematic of the closed cycle gas turbine power plant. So, here you see there are 4 important components. One is compressor, another one is heater, third one is turbine, and the fourth one is the cooler. So, in the compression process, the air is being compressed from a low pressure to a high pressure in the compressor. The high pressure, high temperature air enters into the combustion chamber, and here heat is being added to the air, and the combustion gas comes out from the combustion chamber and it enters into the turbine. Thereby, the turbine does work in the expansion process inside the turbine. So, turbine work is WT, and after that the low pressure, low temperature air enters into the cooler. Thereby, the heat is given out to the system, and after that it enters into the compressor, and in the compression process again the pressure increases from low pressure to a high pressure, thereby it completes the cycle. So the heat input for this total BRAYTON cycle is QH. WT is the work done by the turbine, WC is work done onto the compressor. So here a part of the work done of turbine is used for running the compression. So net work output for the system is equal to WT minus WC. The states of air marked in the schematic and cycle diagram are as follows. The BRAYTON cycle is shown in figure Q consists of the following processes. The first one is 4 to 3, that is the reversible adiabatic compression. 3 to 2 is reversible constant pressure heating. 2 to 1 is reversible adiabatic expansion, and 1 to 4 reversible constant pressure cooling. The heat transfer to the system is QH and the net work output of the system is WT minus WC. Now this is the TS diagram of BRAYTON cycle, temperature entropy diagram. So from state 1 to state 3 it undergoes the compression process, and thereby WC is work input to the system, and 3 to 2 is the constant pressure heat addition QH, and WT is the work done by the turbine, and QL is the heat given out by the air to the surroundings. Now from here we can calculate the efficiency of the turbine, and also we can calculate the other parameters. While figure 3 shows the schematic of the air cycle refrigeration system, figure 4 shows the cycle on which the system works. So we are talking about the reverse BRAYTON cycle. We will see that when the cycle works in the reverse directions, it will work as air refrigeration system. So let us see how it works. It is easy to comprehend from these figures that they are exactly the same as shown in figure 1 and 2, but the direction of heat and work interactions. It is for this reason that the ideal cycle on which air cycle refrigeration works is named as reverse BRAYTON or JOULE cycle. This is the diagram for air cycle refrigeration system, and here you see that the turbine work is from 3 to 4, and that temperature at 0.4 is low, so it is sufficient to extract heat from the confined space which is to be refrigerated. So QL is the heat taken from the confined space which is to be refrigerated, and 1 is the exit point after extracting heat from the refrigerated space, and it is just the entry point of the compression. So 1 to 2 is the process which is going on in the compression. So for that we have to perform work onto the system, that is WC. Now between 2 to 3 is the heat given out by the air to the surroundings. So QH is the heat given out to the surrounding, and The point 3 is the state of air which just about to enter to the turbine. Now let us see how we can calculate for different parameters. This is the TS diagram of the reverse BRAYTON cycle. So 1 to 2 is the compression work and 2 to 3 is the constant pressure heat rejection by the air, and 3 to 4 is the expansion in the turbine, and 4 to 1 is the net heat taken. So 4 to 1 is a process for heat taken from the refrigerated space which is to be refrigerated. Air leaving the refrigerated space at state 1 is compressed to state 2 reversibly and adiabatically. That's why it's known as the isentropic process. The compressor air is then cooled at constant pressure pH to state 3 by passing the air through the cooler. The air at state 3 is then expanded reversibly and adiabatically in the turbine to state 4. So reversible and adiabatic process is known as isentropic process. Here the entropy remains constant. The work output of the turbine WT aids the compression to the extent it can, thereby reducing the net work to be supplied from outside from WC to WC minus WT. Low pressure, low temperature air at state 4 enters the space to be refrigerated to pick up the heat to maintain the refrigerated space at a temperature corresponding to state 1. Here let us perform the calculation part, that is QL, that is the net refrigerating effect, is equal to H1 minus H4 is equal to Cp multiplied by T1 minus T4. WC is the work done by the compression is equal to H2 minus H1 is equal to Cp multiplied by T2 minus T1. QH is the heat given out by the air to the outside is equal to H2 minus H3 is equal to Cp multiplied by T2 minus T3, and WT is equal to H3 minus H4 equal to Cp multiplied by T3 minus T4. So here we can calculate the work done by the turbine, the work done by the compressor, the net refrigerating effect QL, and other parameters also. Now let us perform some calculations for calculating the temperature. Now let us see that what expressions we get with the relations between the pressure ratio and the initial temperature of air before compression and the final temperature of air after compression. So we know that pH divided by PL is equal to T2 by T1 to the power gamma divided by gamma minus 1. So gamma is the ratio of specific heat of air at constant pressure and the specific heat of air at constant volume. So that is equal to T3 by so P2. So pH by PL is equal to T2 by T1 to the power gamma divided by gamma minus 1 is equal to T3 by T4 whole to the power gamma divided by gamma minus 1, and COP is net refrigerating effect by the net work done. So that is QL divided by WC minus WT, that is equal to T1 minus T4 whole divided by T2 minus T1 minus T3 minus T4, and the refrigeration capacity is equal to m dot multiplied by Cp multiplied by T1 minus T4, and the compression power is equal to m dot multiplied by Cp multiplied by T2 minus T1. Here m dot is the mass flow rate of air within this cyclic process. The above cycle is only an ideal cycle, and hence the irreversibilities in the compressor and turbine are not considered. The actual practice, because of irreversibilities, the temperatures at the end of compression and expansion increases, leading to the decrease in COP of the system. The COP, that is the coefficient of performance of the air cycle refrigeration system, is low. In spite of this, it is used in aircraft cooling as it has the advantage of lower weight compared to an equivalent capacity vapor compression refrigeration system. And also because there is no need for an additional compressor for the cooling system, as the required compressed air can be bleed from the main compressor of the jet engine. So for this case there is no need of extra compressor, because in the jet engine we can bleed the compressed air for this air refrigeration system. So let us see how aircraft cooling system works. Shown in figure 5 is the schematic of a simple system used for cooling aircraft cabins. As air bleeds from the jet engine, compressor is passed through the heat exchanger, cooled by the outside air. This cooled high pressure air is then expanded in a small turbine. The work from the turbine can be used to run the fan that sucks the air over the heat exchanger. The air emerging out of the turbine at low temperature is passed through the cabin. The bypass line is used for temperature control. So this is the schematic diagram of the reverse BRAYTON cycle. So in this case you see that air from the compressor is bleed and it is used for this reversed BRAYTON cycle. So here you see that the turbine, the output of the turbine is used to run the fan, and the fan sucks the air, and the air which is coming out from the turbine is being used for cooling purpose. It is sent to the cabin for the cooling purpose. The detailed discussion we have already had while discussing the reverse BRAYTON cycle. Now let us see this block diagram for the gas refrigeration system, and you see that the compressor is there for the compression of the air from state 1 to state 2, but when we use for the aircraft refrigeration system, the separate compressor is not needed. Only we need the compressed air which is already there from the gas turbine engine. So at state 2, when the air is compressed, temperature will be more, so it is passing through the cooler and the heat is given out to the outside, and after that it is passing through the expander, and instead of turbine we will say the expander, because expansion takes place, and because of the expansion the pressure decreases and temperature will also decrease. So 3 to 4 is the process which is going on through the expansion process. After that, it is the low temperature, low pressure air passes through the refrigerator, and thereby the heat is taken from the refrigerated space which is to be cooled down. And the one is the exit point of the air after taken heat from the confined space which is to be cooled, and after that it is entering into the compressor so that its temperature and pressure will increase while passing through the condenser. Now this is the TS diagram for gas refrigeration system. So you see that from state 1 to state 3 the expansion process takes place in the turbine, but for the air refrigeration system we will call it expander instead of turbine. So WT is work done by the turbine, and from 4 to 1 here heat is being extracted from the confined space which is to be cooled, and 1 is the entry point of the compression, and from 1 to 2 the compression of air takes place, and here you see that WC is the work done for the compression process, and 2 to 3 again the heat is given out to the surrounding. So in this process it is continuously taken heat at a low temperature region, and it is heat given out to the during the process 2 to 3, that is Q2, heat is given out to the surrounding. So here again at the point 3 to 4 there is expansion of the air in the turbine process or expander, thereby temperature drops down. Because of the low temperature it can extract heat from the confined space, because heat will always flow from a high temperature region to a low temperature region. This is a schematic of aircraft cabin cooling. Now you see that from 3 to 4 the compressed air is passing through the air turbine, and thereby its temperature drops down, and the low temperature air is passing through the air cabin, and the output of the turbine is used to run the fan so that it can suck the ambient air. And see at the point 2 that the pressure P1 is the compressed air. Actually it is coming from the compressor which is there in the jet engine. We call it bleed from main power plant compression, and that actually enters into the turbine, and there is a bypass control system is there if that the cabin pressure has to be maintained to a particular limit. So that's why that high pressure air which is coming out from the compressor, it can be used for maintaining the cabin pressure inside the aircraft. So you know very well that when the aircraft is moving in a very high altitude, the outside pressure is low, outside temperature is also very low, but we have to maintain required pressure as well as the temperature for human comfort. So for that we have to supply air will be suitable for human comfort, and it has to be maintained at a constant pressure. So This is the schematic diagram. If you look at, then you will find how it works. So this is the diagram for the open cycle aircraft cabin cooling. So this diagram is the TS diagram, that is temperature entropy diagram. So you see that point 3 to 4, this is the expansion process inside the turbine or the expander, and during the expansion the temperature drops down, and that temperature having very low temperature. So if the air passes through the expander, then from the point 3 to 4, the expansion of air takes place inside the turbine or expander. Then at point 4, its pressure is P2 and the temperature is very less, and that air is being used for aircraft cabin cooling purpose. And this is the temperature entropy diagram for open cycle aircraft cabin cooling. Now let us see how we can solve numerical on this topic. In an ideal air cycle refrigeration system, air enters the compressor at 1 bar 5 degrees centigrade and is compressed to 3 bar. The air is then cooled at constant pressure to 50 degrees centigrade and then expanded in a turbine to 1 bar. The cooling capacity of the system is 10 kilowatt. Assume air behaves as a perfect gas with Cp is equal to 1.005 kilojoule per kgK and Cv is equal to 0.718 kilojoule per kgK. Find COP, mass flow rate of the air, and the power required by the system. Dear learners, when you solve any problem, first you note down the data which is given for this particular problem. So in this particular problem, the specific heat at constant pressure is given, that is equal to 1.005 kilojoule per kgK, and the specific heat at constant volume, it is also given as 0.718 kilojoule per kgK. With these values, you can calculate the gamma. Gamma is equal to Cp by Cv. If you put these values, you will get the value of gamma is equal to 1.4. The initial pressure is 1 bar. Final pressure of after the compression in the compressor is given as 3 bar. So the pressure ratio P2 by P1 is equal to 3. The initial temperature before compression is given as 5 degrees centigrade. The final pressure after the compression process is also given as 50 degrees centigrade. Now let us see how we can solve this numerical. This is the TS diagram for exercise 1. So when you solve any problem, it is better to draw the TS diagram, that is temperature entropy diagram. Here you see 1 to 2, this process is isentropic compression process. We call it reversible adiabatic compression. 2 to 3 is the constant pressure heat rejection process. 3 to 4 is reversible adiabatic expansion, and 4 to 1 is constant pressure heat addition, or H1 minus H4, we call it, this is the net refrigerating effect. So in this case, there is compression work, that is equal to H2 minus H1. There is turbine work, that is equal to H3 minus H4. There is net refrigerating effect, that is H1 minus H4. Now, dear learners, let us see how we can proceed further for solving this very interesting numerical. From the data, T1 is equal to 273 plus 5, that is 278 Kelvin. P1 is the initial pressure is 1 bar, P2 is the final pressure, that is equal to 3 bar. So T3 is also given, that is equal to 273 plus 50, that is 323 Kelvin. Now the capacity for this refrigeration system is given as 10 kilowatt, and gamma, as I already mentioned, it is the ratio of specific heat at constant pressure divided. It is the ratio of Cp and Cv. Cp is specific heat at constant pressure and Cv is specific heat at constant volume. For this case, we will get the value of gamma is equal to 1.4. Now T2 by T1 is equal to Ph by Pl to the power gamma minus 1 by gamma. So T2 we can find out from this expression that comes out to be 380.5, because we know the ratio of pH by PL, that is 3 by 1 equal to 3. We know the value of T1, so there is no problem for calculating the value of T2. Similarly, for the reversible adiabatic expansion, T3 by T4 is equal to pH by PL whole to the power gamma minus 1 by gamma. So T4 we can calculate from this expression that comes out to be 236 Kelvin. Refrigerating effect is equal to Cp multiplied by T1 minus T4. If you put the value of T1, T4 and Cp, the refrigerating effect for this particular case will be equal to 42.21 kJ per kg. The net work W is equal to Wc minus Wt required for running the compressor, that is equal to Cp multiplied by T2 minus T1 minus Cp. So the net work, that is equal to Wc minus Wt required for running the compressor is equal to Cp multiplied by T2 minus T1 minus Cp multiplied by T3 minus T4. So we know T1, T2, T3 and T4 and the value of Cp, that is equal to 1.005. Put all these values, find out the value for W, that is equal to 15.6 kJ per kg. The COP, that is coefficient of performance, is equal to refrigerating effect divided by the work done, that is equal to 2.7, because we know what is the value of refrigerating effect, we know what is the work done. So the mass flow rate is equal to capacity by refrigerating effect. For this case it is equal to 0.237, because we know the capacity that is given for this problem, that is 10 kilowatt. The refrigerating effect that we have already calculated, 15.6 kilojoule per kg. The power required is mass flow rate multiplied by the work done. For this case, power required is equal to 3.7 kilowatt. Now, dear learners, we have discussed the gas compression refrigeration system. We have discussed the BRAYTON or JOULE cycle. We have also discussed the reverse BRAYTON cycle, and lastly we have solved some numerical, so that whatever we have discussed we can apply the theory which we have learned through this lecture session, how we can apply for solving the numerical related to gas compression refrigeration system. Thank you.